Okay, we will be starting chapter 2, and the focus of chapter 2 is primarily limits and the new concept of a derivative. In this section, we're just going to look at an introduction to limits. Okay, the difference between calculus and algebra is that algebra is very static. It's kind of at one point in time. We're not talking about something that's changing and moving. Calculus gets into something more dynamic where things are changing and moving, and that change is what's really the focus of calculus. Okay, if we look at the limit of a function, I want you to get a good idea of what a limit is. So a limit is not the actual value of the function at the point in question. It's what is happening as a particular value is getting closer and closer, as the domain is getting closer and closer to a particular value there. So for instance, if we look at this function here, I want to look at the limit as x approaches 2, and this is a little arrow, approaches 2 from the function 2x minus 1, okay? So what we've done here in this table is kind of looking at, if we want to look at the limit, we don't really want to know what happens to it when we plug 2 in. We don't care about that. We want to know what happens to the y values, which these are the y values, as we get closer and closer to the number 2. So if you think about, here's 2, as an x. So we want to pick numbers that get closer and closer to the number 2 from the upper side and also from the lower side. So there's nothing special about these numbers here other than each one is getting closer and closer to 2. Same thing this way. We're getting closer and closer to 2 from the upper side. So these values represented here in the table are just simply, if I plug 1.5 into this function, I'm going to get 2 out of it. If I plug 1.9 in, I'm going to get 2.8 out, and so forth. So what the limit is, this represents your domain, okay? So when the domain is getting close to 2, what is happening to the actual value of this? So what is the y value of this getting closer to? So if you look at these numbers and kind of follow it in, as these numbers approach 2, the f of x numbers are approaching the number 3. Okay, same thing over here. As the x's approach 2 from the upper side, the y values or the f of x values are approaching 3. Okay, so because it approaches 3 from both the bottom and the top, then we would be able to say that that limit is 3. So in this particular one, if I plugged 2 into this, I would get 3 out. So sometimes the function value and the limit are the same, but they don't have to be. And that's kind of what we'll see as we go through this. Okay, so if we looked at the function f of x equals x plus 2, that's just a line with a y-intercept of 2 and a slope of 1. And you can see that it's graphed here. And if we look at this here, if I'm looking at the limit as x approaches 2 of the function x plus 2, then what happens is these x values are going to get closer and closer to 2. So let's say we start out here. If I follow this up to where it hits the function and then over, okay, and then we get a little closer to 2 and we follow that up and over, then what we want to do is we want to see what are these values getting closer to. So as we get closer to the 2, the actual function value is getting closer to 4 from the lower side, and same from the upper side. If we start here, we're up here closer to 5, but when we get a little closer into 2 down here, then we get closer to 4. So coming from both directions, we're getting closer to the number 4. So 4 would actually be the limit here. Okay, if you have a function, so it says let f of x equal x plus 1, discuss the behavior of the values of f of x when x is close to 1. So that's just another way of saying find the limit as x goes to 1. So you could create this on your calculator using tables. So I wanted to talk to you for just a minute about how some helpful tips for doing that. So if you go to the y equals menu and put your function in, and you can't really see, but there's an x here. So we've got x plus 1, that's our function. So we're going to type it in here. And then if you go to the next thing you would want to do is, and I've got these a little bit out of order, but you want to go to table set. Okay, so table set is the second function of the window button. Okay, so on the table set, I usually just started at 0. Since 1 is what you're interested in here, you could also have started it at 1. That would be fine. It's really not going to matter if you do it what you're starting these at. If you choose for the input, if you choose ask, if you put auto, then it's going to start at 0 and go up by tens, and that can be helpful, but for this particular problem, it's better if you choose ask, because what it's going to do is it's going to let you choose your x's. So if I want to know what the behavior of the function is as x approaches 1, then I want to fill this x column in with values that are getting closer and closer to 1. So you can see I've picked like 0.9, 0.99. So each step of the way, I'm getting a little bit closer and closer to 1. Okay, so 1 would be in here. I didn't put 1 in because the limit does not have anything to do with what happens at the value of 1. It has to do with what's happening as it gets close to 1. So same thing on the upper side. If I start at 1.1 and then just choose incrementally values that get closer and closer to 1, then you can see that these values here, if I'm looking, these are getting closer to the number 2. And same thing here. These are getting closer and closer to the number 2. So the limit for this one would be 2. So a table is a viable option for finding the limit. It would not be my first option. This would be something I would go to when I've exhausted other algebraic methods, which we're going to look at later today. Okay, if we have something like the absolute value function, if we know that the absolute value function basically is the positive regardless of what we put into that. So let's look at this graph here. If we've got the function h of x is equal to the absolute value of x over x, okay, I've put the graph in for us to look at. So if I look at this particular function, h of x is equal to the absolute value of x over x, we want to consider this as we approach 0. Okay, so the limit as x approaches 0. Well, the graph, if I'm looking at this graph here, if I tried to plug 0 in, I'm going to get 0 over 0. So that's an undefined statement. And so that's where I have to use other methods like the table or the graph to be able to figure these out. So looking at this, we've actually got an open circle here and an open circle here. So if I'm looking at the limit as we approach 0 from the right side, okay, that's over here coming in towards 0, then this function is, follow the graph, is getting closer and closer to positive 1. But if I approach 0 from the left side, then I'm down here and it's getting closer and closer, or it's actually at -1. So if I approach from one side, it's at 1. If I approach from the other side, it's at -1. So what we have to say is that the limit does not exist, and we'll abbreviate that simply D and E. Okay, so anytime one side of the limit does not equal the other side of the limit, we have to say that it just simply, the limit does not exist. And you could put this in to look at on your calculator. If you need to go to the absolute value function on your calculator, it's under the math menu, and you choose number 1 for ABS, and it'll give you a graph that looks something like this. And you can see if you go and set up a table, which is also another viable option here. If I'm putting anything in below 0, then I get -1. If I put anything in above 0, I get +1, and if I put 0 in itself, it gives me an error because it's not defined there. So because one side is going to -1 and one side's going to +1, the limit doesn't exist. So that's just if you were to do it on the calculator. Okay, if we look at this one here, again, this has an absolute value in it. So this one's asking for the limit as we approach 2. So that means if we're looking at it as if we approach 2, if we're approaching 2 from this direction, then that means that the limit from the upper side would be 1. If we approach from this direction, then it's approaching -1. Remember, limits are always y values, okay? So we want to know what is the y value as the x gets close to 2. What is the y value getting close to? In this case, it's staying at 1 or it's staying at -1. Either way, they don't equal each other, and so this would have to be a does not exist type problem with this, okay? You could do the table as a way to see this as well. Okay, we can have what's called one-sided limits. So especially when a limit does not exist, it's helpful to look at what's called your limit from the left or your limit from the right. So if you see a little negative that follows the number, not before the number, because that would just be a regular negative. If you see a little raised negative after the number, then that says take the limit coming from the left, okay? And if you have a little positive sign there, that means you want to look at the limit from the right, or sometimes they're called the left-hand limit and the right-hand limit. And if you don't see a little plus or minus, then you do have to consider both sides when you're looking at the limit. Okay, so looking back at the example that we looked at a couple minutes ago, this particular one, what we could do is we could say that the limit as x approaches 0 from the right side, okay, so coming in from the right side for this particular function would be equal to 1. The limit as we approach from the left side, that's going to be this -1 down here. But then the limit as we approach 0, where we don't specify a direction, would be equal to does not exist. So it really depends on, are you only looking at the right side, are you only looking at the left side, or are you looking at both sides? Okay, so we're kind of building strategies for evaluating limits. And the first two, graphing and tables, are definitely ways to evaluate limits. So if you're given a graph and you're not really told what the particular function is, it says use the graph to discuss the behavior of f of x for x near -1. And okay, so here at -1, this is what we're looking at. We want to consider if we're getting close to -1 from both the left, and if we're getting close to -1, actually, this would be from the right, and this would be from the left, okay? So if we're following the graph coming in from both directions here, you can see it actually is converging on the value of +1. So we could say that the limit as x goes to -1 for this particular function is equal to 1. And we could also say the limit as x goes to -1 from the left is equal to 1. And we could say that the limit as x goes to -1 from the right is equal to 1. So when the overall limit is equal to a particular value, then that indicates that both the left and the right limits are the same as the overall limit. Okay, so same graph, but this time we're looking at it as it goes to 1. Okay, not -1. All right, so over here, if I'm looking at this graph as it approaches 1, I'm going to come in this way and I'm going to come in this way. So that means if I'm following this graph Okay, it looks like it's heading up to 3 if I'm coming from the right. And if I'm following this side, it also looks like it's going up to 3. So even though there's an open circle there, so the function's not actually defined at 1, but the limit does equal 3. Okay, so we don't really care what's happening at 1. We just want to know as it's getting close to 1 on either side, what are those function values getting close to? They're getting close to 3. And so the limit from the left would be 3, the limit from the right would be 3 on this one. Okay, so let's look at this one as we approach 2. So if we're looking at the limit as we approach 2 for this particular graph, okay, so we're going to come in, we want to come into 2 from the right side. So we'll look at that one first. Okay, if I'm coming in from the right side, that means I'm up here, okay, following it in toward 2, but following the graph. So it's actually taking me to 5. But if I look at the limit as I approach 2 from the left side, okay, that means I'm coming in this way. So I've got to follow my graph in. Okay, I'm going to turn. I'm going to go back down here. So it looks like I'm getting closer and closer to 2. Okay, since these don't equal, then that means the limit as x approaches 2 of that function does not exist. So the right limit is 5, the left limit is 2, the overall limit does not exist. Okay, this would be a good place for you to pause and practice, and then we'll look at the answers on this. Okay, on this one, if we're looking at it approaching -1, oh, this one's not defined for values less than -1, so we can really only look at this one side here, and we'll see that when we look at that, when we look at this, the limit as we approach -1 is going to be 2 because it's not defined on the other side, so we can't even look at that other part. We're looking at the limit as it approaches 1, then that means we're coming in from the right side, we're going to be at 2. So the limit as we approach 1 from the right is 2, and the limit as we approach 1 from the left is going to be 1 because that's going to take us up here. Okay, and so we're going to be at 1. So the limit as x approaches 1 overall simply does not exist because these two values are not the same. Okay. All right, if we're looking at the limit as we approach 3, okay, the limit from the left side, if I'm coming in to 3 from the left, then that's going to be here at 3. And if I approach 3 from, sorry, if I approach 3 from the right, it's going to be 3. And if I approach it from the left, it's also going to be 3. Okay, so that means that that overall limit is 3. So even though there's an open circle here, that's fine. If there happened to be a point up here, that's still fine, but the limit's 3. Okay, so even if that point's stuck up here somewhere, that's not your limit. Your limit's down here. Okay. All right, so the limit as we approach 4, a lot of people want to tell me there's no point there. Well, there's infinitely many points here, okay? So yes, if that line is drawn in, there is a point there, and it looks like that point's going to be at 3. So no matter whether you're approaching from the left or from the right, it's still going to be at 3. And you notice here, one thing notationally, you want to say things right. So if you're talking about the limit, you'll say does not exist. But if you're talking about a function value, you'll just say it's not defined. So like on this one, it was not defined at 3. okay, because that wasn't there, so it would not be defined at 3. We've got open circles above the 1, so it's also not defined at 1. So kind of keep that terminology correct. Okay, so direct substitution is another strategy for evaluating limits, and this is probably the easiest one because basically what it says is if you plug in what you're approaching and you get something that's not undefined or like 0 over 0, then that's your limit. Okay, so it's not anything too profound. You can add two limits together, you can subtract two limits, you can multiply a constant times a limit, and it's going to basically work like you expect it to. Okay, so I don't want to over dramatize this. Okay, so let's look at some examples here. If I've got something like this, okay, so by our properties that we just looked at, that would be equal to the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 3x. But as you go and do these, a lot of times you don't write it out like this as often. I mean, generally you'll just do this all at one time. So essentially, I'm just going to plug the 2 into this. So if I plug 2 in, I'm going to have 2 squared minus 3 times 2. So 4 minus 6 is negative 2. And negative 2 is fine as as an answer. And so we're just going to leave it at that. Okay, if I look at this one, then I could break it apart with those properties, but essentially I'm just plugging this in. So 2 times 4 over 3 times 4 plus 1. So that's going to be 8 over 13. And that's fine. There's nothing wrong with that. Okay, here's one for you to try. I will say be careful when you're squaring something like this because if I'm evaluating this, what I'm going to see is it's going to be negative 2 squared plus 5 times negative 2. So that'll be 4, a positive 4 because the negative gets squared as well, minus 10. So I'm going to end up with negative 6 for my answer. Okay, if we have a limit of a function and the function is a polynomial, then that's another one you could basically do with, I mean, that's one you could do with direct substitution, essentially is what it's saying. And same thing with a rational function, so long as you're not evaluating it where the denominator is equal to 0. Okay, so that's basically what that says. Okay, so these, if you were to look at them, you're just evaluating it by plugging in. So the limit as x goes to 2 would be 2 times 2 to the 4th minus 3 times 2 squared plus 1. And if I do all the calculations there, I'm going to get 6 for my answer with that. This one, again, just plug in. So that's going to be the cube root of 2 times 1 to the 4th minus 3 times 1 squared plus 1. So I'll have the cube root of 2 minus 3 plus 1. So and actually I just realized this would not be 6. This would be 21. I looked at the wrong answer on my paper there. Okay, so this one would be the cube root of 0, which is in fact. Okay, so on some like this, these are rational functions. So as long as we're not looking at evaluating the limit as it approaches the value that makes the denominator 0, we're fine to just plug in. So this would be 2 times 2 plus 3 over 3 times 2 plus 2. So that would be 4 plus 3 would be 7, and this will be 6 plus 2 would be 8. So 7 over 8. This one, even though it looks kind of like we've looked at this one before, but we looked at it as x approaches 0. This time we're looking at it as x approaches 4. So if I plug 4 in, there's actually nothing wrong with that. Okay, so that limit would be 1. Okay, here's some for you to practice on. I'm not going to go through each step here, but just be sure like that you can plug these in and check. So this one, if you plugged in, should give you 6. This one, if you plug 2 in, is going to give you the square root of 6. And this one, if you plug negative 2 in, again, be careful with your signs. Negative 2 squared over negative 2 squared plus 1 would be 4 over 5. Okay, the next strategy is the piecewise defined functions. We've talked about piecewise defined functions, but they're a little bit different when you start talking about limits. So if we have, I'm going to go ahead and bring these up here so we can see. So we have this function defined in 2 pieces. So if x is less than 2, then I'll use the first function. If x is greater than 2, I'm going to use the second function. Okay, so looking at this one, I'm asked to find the limit of f of x as x approaches 2 from the left. Okay, so if I'm approaching 2 from the left, I'm talking about like 1.9, 1.99, things like that. Okay, so if I look over here at the domain, I need to figure out where numbers like this fit. Do they fit here or do they fit here? Okay, they're less than 2, so that means they fit here. So I'm going to plug into the first piece of this piecewise defined function. Okay, so I'm going to have 2, because 2 is the number I'm approaching, so 2 squared plus 1 is going to give me 5 for my left limit. Okay, if I'm approaching 2 from the positive side or from the right side, then that's stuff like 2.1, 2.01. So that's going to be using the second piece. Okay, so if I'm using the second piece and I plug 2 into the function, I'm going to have 2 minus 1 because I'll use this piece. So x minus 1, 2 minus 1 is going to give me 1. Okay, so then the next question is, well, I've done my left limit, I've done my right limit, so what's the overall limit? These don't equal each other. Okay, so since they don't equal each other, we're going to have to say that this one does not exist. And then the last is actually not talking about a limit, is talking about a function value in particular. But if we notice, there is no piece defined when x is actually equal to 2. So what we're going to have to say here is that it is not defined. Okay, this is a graph of it, just in case you want to see what's happening with it. And you can see here at 2 that we have one value coming from the right, one from the left. They don't equal, so we don't have an overall limit there. Okay, here's one that you could definitely try. If we look at this one, if you're approaching 5 from the left, then that would be numbers that are less than 5. So that tells me that we need to plug into the first piece. So 2 times the 5 plus 3 looks like it's going to give us a left limit of 13. If I'm using values to the right of 5, that would be like 5.01, 5.001, then that means I'm going to have to use the second piece. So that would be negative 5 plus 12. So I'm going to have 7 for that limit. Well, these don't equal, so this means it does not exist. And there's also not a place where it's evaluated at 5. So because of that, we're going to say this is not defined. Okay. Now, if one of these had an equals, let's say it had an equals here, then that would mean I could plug the 5 into this piece and get the function value. So that would be 2 times 5 plus 3. So that would mean a function value of 13. But since it does not, it's not defined anywhere, you're going to say not defined. Okay, and again, this is the graph if you want to take a look at it. You can see that there's a gap. So anytime we have a break in the graph where they separate like that and they're not connected, you're not going to have a limit. Okay, so the limit of a quotient. This can be a little bit tricky here. So I want to take a look at it. Okay. This one, if I were to, actually, I'm going to come back to this. Okay, the last strategy that we're going to look at today is dealing with indeterminate forms. So indeterminate forms occur when we have a rational function that ends up being 0 over 0. So if I have something that's 0 over 0, I can't determine what the limit is without having to do some additional work. And I'll show you what that additional work is going to look like. Okay, so let's say we have something like this. So the first tendency would be to just do direct substitution. So if I do direct substitution, I'm going to have 2 squared minus 4 over 2 minus 2. So I'm going to have 0 over 0. Well, I can't divide 0 by 0, so I've got a problem there, okay? So when we have this indeterminate form, okay, what I want to do with it is to actually try to factor this. Keep bringing the notation down because you need to keep writing this until you actually do take the limit. But we're going to try to factor it, okay? If it's possible to factor. So if I factor this, this is the difference of squares. So it's going to factor as x minus 2 and x plus 2. Okay, so now what we see is that we have a common factor, and that'll happen a lot of times. So we're going to take out those common factors. And so now all of this is equal to the limit of just the x plus 2. Okay, so take out the part that canceled out. So when I plug in the 2, now I'm going to have 2 plus 2 is going to give me 4, and 4 is my limit. So even though it's an indeterminate form here, you don't stop. You need to keep going and try to factor and see if you can cancel a common factor out. If for some reason you could not cancel a common factor out, that's when you would go to like your graphing on the calculator or your tables on the calculator and see if you could find the limit some other way. Okay, if we look at this one, this looks very similar to the one that we just did, but if I do this one and plug in the 2, I'm going to have 2 minus 2 over 2 squared plus 4, okay? So that's going to be 0 over 8. 0 over 8 is just 0, and 0 is okay, all right? So it's not an indeterminate form, so 0 is okay as a limit. It's only when it's 0 over 0 that you have a problem. Okay, this one would be one, if I tried to evaluate it, I'm going to get 2 minus 2 would give me 0. 2 squared would be 4 minus 4 would be 0. So this would be another indeterminate form. So if I look at the limit as x goes to 2, let's try to factor it. Okay, so what happens here is these x minus 2's cancel. So it's equivalent to the limit. I have a 1 that's left as an understood 1 in the numerator, and then I have the x plus 2 in the denominator. So don't forget that 1. So then when I evaluate it, I'm going to get 1 over 4. 2 plus 2 would give me 4. Okay, this one, it looks very similar to what we've been working with, but if we plug in to this, we're going to see that we get 4 over 0. So 4 over 0 is not an indeterminate form. And in fact, anytime you have a numeric value over 0 like that, what you're going to say by theorem 4, which you don't need to remember the number of it, is you're actually going to say that the limit does not exist. Okay, we have a few to practice with. Again, this would be a good time to pause and give it a try. Okay, the first one here, we think about all the strategies that we've talked about, tables, graphs, direct substitution, your indeterminate forms, your piecewise defined functions. So looking at this one, what we see is if I plug 3 in, I'm going to have 3 plus 1 is 4. If I plug 3 in the denominator, I'm going to have 6. So I end up with 2/3, and so that's my limit. I don't really have anything else to do. Here, if I plug 3 in, I'm going to have 3 minus 3 is 0. If I plug 3 in the denominator, I'm going to have 18. 18 over 0 is fine. So 0 is my limit. On this one, if I plug 3 in, I'm going to have 0 over 0, which is an indeterminate form. So this is one that I do need to factor. Okay, so I factor x minus 3 and x plus 3, and then over x minus 3. The x minus 3's will cancel. And then so it's equivalent to the limit as x goes to 3 of x plus 3. Again, don't drop the limit notation. Continue to do that until you actually take the limit. So here, if I plug 3 in, I'm going to get 6 as my answer. Okay, we want to look at limits in relation to difference quotients because this actually speaks to and leads us into talking about derivatives a little bit later. We've talked about difference quotients before, so the first thing we want to do is, I'm not really going to even worry about this limit part here. I'm just going to apply the difference quotient first. Okay, so the difference quotient tells me I'm going to take this function I've been given and I'm going to plug in a plus h for the first part. So I'm going to write down the limit part. Okay, so if I plug in the a plus h, I'm going to have 2 times a plus h and then minus 3. Then I'm going to subtract from that f of a, which is 2a minus 3, and then I'm going to divide that by the h. Okay, still haven't taken the limit, so I've still got to drag this notation along. I'm going to simplify here, so 2a plus 2h minus 3, distribute the negative. Remember, on these difference quotients, we're always going to see the second part of it get canceled off, so the 2a's and the 3's get canceled. Again, I haven't taken the limit, so I'm still dragging this along. I've got 2h over h. Sorry. All right, so the h's cancel. And this is one thing we haven't really looked at. If we just have a constant and there's nowhere to plug in to take the limit, then that means it's just the 2. Okay, so just whatever is here, there's nowhere to plug in, then that's what your limit's going to be. Okay, so looking at this one here, we want to do another difference quotient. This one actually has numbers instead of the a in it. I'm going to do the same thing. I'm going to write the limit as h goes to 0, and then I'm going to simplify this part here. So in the place of the x, I'm going to put in 4 plus h. So I'm going to have 7 minus 2 times 4 plus h, and then I'm going to do minus f of 4. So f of 4, I could just go ahead and find that. 7 minus 2 times 4 would be -1. So I get 1 minus from the difference quotient itself, and I get another minus from the fact that this is -1, and that's all over h. Okay, we haven't taken the limit, so keep dragging the notation along. I'm going to distribute here, so -8 minus 2h plus 1 over h. Okay, 7 and 1 will give me 8 and a -8, so all those cancel. So I've got the limit as h goes to 0 of negative 2h over h. The limit as h goes to 0 of negative 2 is going to be equal to negative 2. We're not going to do any that are super difficult with this difference quotient, but you should be able to understand your function notation. And then the very last step, you're just going to keep dragging this limit notation along. And the very last step, you're going to apply the limit to it. Okay, that's the end of this introduction to limits. There was a lot that we went over today. Just make sure that you have a good understanding of limits, and we'll continue with this in the next section.